couple of announcements before we get started. Let me just see if I can turn the volume down here. Is that okay? All right, nice. So yeah, homework 3 is due today, and then project 3 will be due next Tuesday. Homework 4 will be out later this week, due next Friday, and just sort of a friendly reminder that 2 weeks from today will be the midterm, so there's more info on the website. We'll have like review sessions, and we'll have like discussions that'll help you prepare for that. So yeah, keep an eye out for the announcements posted on Ed. Today we're going to talk about Bayes nets, which is going to build on the lecture from last Thursday. And essentially what we're going to be doing is we're going to be building these concepts, or building these models out of the concepts we learned in probability so that we can help ourselves answer detailed questions about uncertainty. So this idea of taking the concepts from probability and leveraging them and making them work for us. So just to recap what you guys talked about with Michael last time, there's some basic rules in probability, and one of those rules is that there are events that can happen, and when an event happens, it makes the set of possible worlds, it'll sort of restrict that to whatever actually happened. Each of these events is associated with a probability. That probability has sort of a likelihood of occurring, and these numbers exist between 0 and 1. They have to sum to 1, all these sort of like classic probability things, right? We can have events, we can talk about events. An event is just a subset of the possible worlds that meet a certain condition, right? So if we have this event A, it might be like, I made it to lecture on time, and it could have been done in any number of ways, right? I could have taken the bus, I could have walked here, I could have taken the train. The event A just means I got here in time, and it doesn't really matter how we did that. But each of the probabilities associated with, me getting here by taking the train, me getting here by walking, me getting here by riding my bike, has a probability, and then the total of the probability for all the events, all the outcomes that are consistent with that event, that's what we're trying to add up here. We'll also talk about like random variables. We give these capital letters like x, and we say that these are functions that take in an outcome and tell you a value. So each of these values now, each of the values that a random variable can take on has some associated probability with it, and that's going to be dependent on which outcomes have which values. We can also sum out if we have a joint distribution for p of x and y. We can sum out to get the marginal distribution for x or the marginal distribution for y. All we have to do is add up all the different ways. This is sort of like, how did I get here? We add up all the different ways that we could see the variable y manifesting itself, and then what's left is just x, right? So that's the probability distribution over x. And the way that we compute that is we just add things up. We also talked about conditional probability distributions. So this says if I have some information, y, and I want to figure out some information, x, I can model the probability distribution of x conditioned on y by thinking about all of the events where y is true as sort of like my normalizing constant. This is like the total probability that's available if y is true, or the total probability that is available if y is false. And then I look at all of the events in the joint distribution x and y, and I take the subset of the ones that match my sort of xy condition, right? So this is just the conditional probability from last time. And you can also rearrange this to get this product rule that says p of x given y times p of y is equal to p of xy, the joint. And you can do it in either direction. So p of y given x times p of x. And this is just Bayes' rule. And this also allows us to write sort of arbitrarily complex joint distributions in terms of a product of their sort of conditional probabilities. So p of x1, x2, x3, xn is just multiply the conditional probability distributions for each one, and then condition on all the variables that came before that. Okay? We also talked about independence, and I wrote strict independence here because in a few minutes we're going to talk about conditional independence, and we'll contrast the two. But independence is basically two variables are independent if it's the case that the probability of x and y is equal to the product of the two marginals, p of x and p of y. So the joint distribution factors into these two different marginal distributions, and you can multiply them together. Or we could also write it this way. We could say that the conditioning information doesn't change what we know, right? So if I have this conditional distribution p of x given y, and I find out, that y is true, that doesn't change my distribution over x. So learning y doesn't tell me anything interesting about x. Or learning x doesn't tell me anything interesting about y also. So all these things are equivalent. And so like an example of this is you roll a six-sided die 2 times, and the probability that you get a 5 on the first roll doesn't affect the probability that you get a 3 on the second roll, right? So the two die rolls are independent because of the way that the physics of these dice work, right? So one die roll doesn't affect the next one. And so basically, the world doesn't really work like this in general. Like, we have to design these materials like dice and coin flips and roulette tables and slot machines in order to make these assumptions hold, these strict independence assumptions. But when they do hold, it's really nice, right? We can, instead of taking this joint distribution over n different coin flips, we can, which is going to take us exponential space to write down, because there's 2 to the n different ways that all those coin flips can come out. And if we want to write down the joint distribution, we have to write down a probability for each of those possible combinations of coin flips. Now we can say, all right, I know that these are independent coin flips, so I'm just going to write down the probability table for each coin flip separately, and I get n different tables, and each of those tables has 2 parameters. It really has 1 parameter, because they have to sum to 1. So now, instead of 2 to the n, we're looking at something that's n, right? So we've gone from exponential to linear, and that's a huge, huge savings. But of course, this only works when we have these nice materials like dice and coin flips. It doesn't work in the real world, right? So what happens if we try to apply this idea in the real world? So here's this example that we talked about towards the end of last time, right? We have traffic, we have rain, we could be holding our umbrella or not holding our umbrella, and we want to sort of model this scenario. So we model it with this joint distribution, right? The joint distribution specifies the probabilities for each of these outcomes. So each of these variables is binary, and so we have this table. We can put all the probabilities in here. You can check that those sum to 1. And this is our joint distribution. This is like our contingency table. So if I wanted to compute the marginals, how would I do that? How would I get the probability? Let's say the probability that rain is false. How could I compute the probability that rain is false? Yeah. Say it again. Add up the 4 p-values. Which 4? These ones? Yeah, why are these the values that we want to add up? So you're saying add up all these ones. These are consistent with, we said we want the probability that rain is false, right? And so all of these have rain is false, and so the probability of each outcome needs to be added up, and we don't care about any of the other variables, right? So does anyone want to add those up for me? 0.7? Okay, great. So 0.7. Do we know anything else? What do we know? Yeah. We need to normalize. What do you think we need to normalize? No, I think we're okay here. We'll have to normalize when we get to conditional probabilities, but right now we're okay. We can just add these things up. But what else? What other information do we have about the probability of rain? Yeah. Yeah, right. So we also know 0.3, right? Yeah, so that's great. So we can actually fill this table in. We get 0.7, 0.3. All right, so let's do this one more time. Let me ask about the probability that traffic is true. what do we need to do now? Yeah. Yeah, exactly. Yeah, so we look at our table, we find the values where traffic is true, right? Traffic's true here, traffic is true here, so we add up these values, and when we add those up, what do we get? 0.35, that sounds right. Okay, and do we know anything else? 0.65 for false, yes. Okay, so 0.65. Awesome. So we can fill that table in. I'll save you the trouble. We can do this for umbrella as well. So if we were going to try and model this 3-variable system with rain, traffic, and umbrella as being strictly independent, these variables being strictly independent of each other, how could we test that, given what we've already calculated? Yeah? Multiply them together, yeah, and see what? See if that equals the p-value that we have already. Great. Okay, so let's do that. Let's do that for the first entry, right? So let's look at the probability of a rain being false, traffic being false, umbrella being false. And what numbers do I have to multiply? This one, and this one. And does that come out to 0.504? Does anyone know what that comes out to? 0.314. 0.314. Well, that doesn't seem like it's 0.504. Okay. Should we do one more? Let's do this one. True, false, true. We can do it in another color. So true, false, true. So 0.3 times 0.65 times 0.31. 0.06? Okay, so these are not coming out to be the same thing. So that's interesting, right? So what that's telling us, if we fill in this whole table, you'll notice that these are not the same thing as we started with. So we take our joint distribution, we compute the marginal distributions, we multiply them together, they're not the same. So that tells us that we don't have strict independence here. That's saying that the variables are not independent from each other. Okay, but what do we always know that we can do? We talked about this just now. We know that this chain rule thing works no matter whether we have independence or not, right? So we can always write things as a product of these conditional probability tables, and we're building up the number of conditioning variables in each case, right? So rain, we already calculated. We have this probability that rain occurs. And then given that we have rain, we know that we can write down the probability of traffic conditioned on rain. So now let's practice writing down these conditional probabilities. So what about this entry right here? This is the probability that we do have traffic when it's not raining. So what do we have to look at in our table to figure this one out? It's a little more complicated than before, but not so much more complicated. So we know that rain is false. So we can look over in our table and we say, all right, well, conditioned on rain being false, let's start looking at these possible worlds, right? And now we want the probability of traffic being true conditioned on being in this blue box. So let's draw that in red. So the probability that traffic is true is comprised of these two events. So what do we want? We want basically the amount of probability in this red box divided by the amount of probability in this bigger blue box, right? So this is a fraction. This is saying the conditional probability of traffic being true, conditioned on rain being false, is this red box divided by this blue box. So what's in the red box? We get 0.14. And what's in the blue box? 0.7? 0.7. Is that right? And so 0.14 divided by 0.7, let's see. 0.2? Great. 0.2. Do we know anything else? What else do we know? Yeah. Yeah, why is that? Yeah, it's 0.8 right here because this needs to add up to 1. Exactly. So let's clear these things out. We can fill in this whole table. We can do the same thing, right? Let's do it one more with, now we have, so essentially, let's recap what we're doing. We're saying, let's keep track of all the events where my conditioning variable has the value that I want it to take. And then let me look at the fraction of those cases where the particular condition on traffic held, right? So we looked at this one first. Now let's look at, let's say, this one, okay? So this is the probability that I don't have my umbrella when it is raining, but there's no traffic. So what is that? Which numbers do we have to look at in this table? Let's number them 1, 2, 3, 4, 5, 6, 7, 8. Yeah, who thinks they know? Yeah. 5 and 6. So 5 and 6 are these two rows. Okay, and let's take a look. So we want rain to be true. We want traffic to be false. So rain is true. Traffic is false. Yeah, that looks good to me. So 5 and 6. Great. And now what do? We want the probability that umbrella is false. So 5 or 6? Well, we just read it off the table, right? So umbrella is false here, so that means our red box is this probability. So red box divided by blue box. Someone want to calculate that? Yep. 0.2. Okay, so it's 0.2 again. Do we know anything else? What's next to that? 0.8. Great. Okay. So this is pretty straightforward now, right? So we can fill in this table as well. And if we do that, and the clicker works, we get these numbers. And we can check in our table, and those things will match. So how do we check? Well, we could check by doing the same thing as before. Like, let's say we looked at this thing. We want to check. We look at false, 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 given false, false. So you're welcome to multiply those things out, but it should come out to 0.504. And this is really nice. What else do we notice about this conditional probability table? Probability of umbrella given rain and traffic. Any structure in there? Yeah. It doesn't depend on traffic. Yeah, so what do we notice? We see, okay, it doesn't depend on traffic if we know rain, right? So if we know rain is false, it doesn't matter whether traffic is false or true, these two rows are the same. And similarly, if we know that rain is true, doesn't matter what traffic is, these two rows are the same, right? So essentially, this is telling us we have conditional independence. So conditioned on rain, we know umbrella whether we know traffic or not. So we can simplify this table. We can collapse this into this, right? So we take this, we collapse the two rows that are the same, and we get rid of the traffic variable because it's the same no matter what, and then we condense that into a smaller table. So this is the idea of conditional independence. Does that make sense to everybody? Questions so far? Yeah.
One question, the way you got 0.2, why did you just divide 0.014 divide by 0.7? Shouldn't
When we got which 0.2? This one here?
yeah. So the denominator was 0.7, which is all the first four rows. But on the top, no.
Well, hold on. So the first four rows, that might have been over Wait, hold on. Which one are we looking at? So rain given traffic, right? So traffic, so we have these two and we have these two, right? Sorry, rain being false, right? So we were conditioning on rain being false, so we want the first 4 rows. Yeah, so this should be, what was this, 0.7? Okay.
So why did you just divide 0.014 divided by 0.7? Because there's 2 rows that...
It should have been 0.14, not 0.014.
Oh, so it's sum of those.
Yeah, it's the sum of those 2 rows, yeah. Does that make sense? Great. Other questions? Okay, nice. So yeah, so we're going to collapse this big conditional probability table. It's not that big, it's 3 variables, but now it's 2 variables. So right, so we get some savings. And we're going to keep doing this, and this is this idea of conditional independence. So it's saying that we're going to exploit structure. We know that in the real world, like this idea of strict independence isn't going to hold all the time, but maybe we can leverage the fact that some variables depend on other variables, and then they don't depend on third variables, and we can figure out like, if that structure exists, we can use it to our advantage. So conditional independence just adds a third variable. It says x is conditionally independent of y given z if, when we know z, we don't need to know y. Right? So this probability of x given y and z is essentially the same thing as probability of x given z alone. And we can write it the other way as well. We can say the probability of the joint distribution conditioned on z is the product of the marginal distributions conditioned on z. So probability of xy given z is the probability of x given z times probability of y given z. All right, another example. Imagine that I have a toothache and I'm trying to figure out if I have a cavity, right? So this robot's going to help me to determine whether I have a cavity. It's going to inspect my teeth. So we can model this with a 3-variable model. I have a toothache variable, a cavity variable, and a variable for whether this thing catches the cavity, okay? So if I have a cavity, the probability that the probe catches it doesn't depend on whether I have a toothache. My toothache doesn't help this thing catch my cavities. Right? And similarly, me not having a toothache doesn't affect this thing's ability to catch my cavities, right? It depends on whether I have a cavity or not. That's what's going to affect this catch variable. Right? So catch is conditionally independent of toothache given cavity. And similarly, toothache is conditionally independent of catch given cavity. So we can write these in lots of different ways, but there's all these conditional independence relationships for this particular problem. Okay, what about this domain? So now we have a fire in our house, and there's a smoke alarm, and the alarm might go off if there's smoke. What do we think is going to be conditionally independent here? I'll give you this hint. Yeah, keep your hands up so I know. Okay, yeah?
Is it that alarm only depends on the smoke at the fire? Because smoke could be from anything else?
The alarm only depends on the smoke? So how would we write that? Conditionally independent or fully independent? So probability of alarm given smoke, and this is equal to the probability of the alarm given smoke and fire. Do folks agree with that? Nodding heads? Yeah. So this is saying if I know that there's smoke right next to my alarm, I'm pretty sure it's going to go off regardless of what kind of smoke that is. It could be smoke from a fire, it could be smoke from a cigarette, it could be smoke from wherever, it could be smoke from my smoke machine, right? If it gets close to the alarm, it's probably going to trigger the alarm. It doesn't really matter if once I know that I have smoke close to the alarm, there may or may not be a fire. It doesn't really help me figure out whether the alarm's going to go off. So yeah, we can model that this way. Here's another problem. We'll call this one Ghostbusters. Imagine that I have a ghost that's hidden somewhere in this grid. Right now I'm showing you where it is, but let's say that we don't know that the ghost is here. And what you can do is you can click on these squares, and when you click on the squares, you get a color. The color tells you how close you are to the ghost. All right? So if you get a red, you're right on the ghost, probably. The sensor's a little noisy. So if you get a red, you're most likely on the ghost. If you get an orange, you're most likely 1 or 2 squares away. You get a yellow, you're a little further away. Green's even farther than that. Okay? So we're going to click on these squares, and then once you're confident, based on the squares that you've clicked on and what colors you got, that you know where the ghost is, you can click this button to bust the ghost, and then the ghost will go away. Okay? Does that make sense as an idea? So we have this noisy sensor. Sometimes it outputs yellow when it really should be outputting green, but overall, if we get closer to the ghost, it's going to go from green to red. All right, so we can do a little demo of a system that's going to do that for us. So we'll start with uniform probability. This is our prior distribution. This is before prior to doing anything in this problem, we think the ghost could be anywhere. It's equal across all these different squares. And then we're going to make a guess. And let's just say we guess here, and we get a green observation, right? So if we get a green observation, what does that do to the probabilities? It says green means that we're far away from the ghost. So that means that, let's see what the best color is to use here, maybe orange. So that means that like in this region, we don't see a lot of probability anymore, right? So the ghost is probably hanging out in this corner, or maybe down here, one of these corners, right? Not so much in this region. So you can see the probabilities adjust once you get this green observation, even though the sensors are noisy. Okay, so we can keep going. And as we keep going, we're going to make another guess. And let's say that we guess over here, right? And we get this yellow observation in the corner. So what that does is it collapses our probability distribution over possible places that the ghost could be, and oops, try not to advance too fast here. So now we're looking at this zone, right? Because we know we're far away from the green, a little closer to the yellow, and so there's this sort of ridge of probability that we might see the ghost in. Okay, keep going. And so we're going to make another guess, and then we're going to make another guess, and we're going to gradually try and narrow in on where we think the ghost is. So first we're going to guess there. We get an orange. Orange says we're getting even closer. So now we're basically pretty sure we're at this 2 places on the ridge that's right next to the orange. And so we're going to guess one of them, and we're going to get a red. And now we're pretty sure that it's right there. We get a 0.97. And just to be, completely sure before we don't want to bust the wrong ghost or hit the wrong square. So we're going to guess a couple of squares around that red square just to be sure that this wasn't sensor noise. But once we're sure, we're going to go ahead and we're going to bust the ghost. And we'll hit it. Great. Success. Ghost busted. So this is like if we had a 3x3 version of this problem, we can write down all the variables on the slide. And we're going to have a variable for the ghost location. That's one of these 9 positions. We're going to have variables for the color of each square, right? So these are our observation variables. And the ghost can take on one of 9 values. The colors can take on one of 4 values. And so the total probability distribution size, the number of possible outcomes here is there's 9 for each, 9 ghost locations times the combinations of all the different colors, right? So we have, get the pen. We have 9, oh, that's impossible to read. Let's try this. 9 times 4 different colors times 9 to the 9th number of positions, right? So 9 times 4 to the 9th. And the way that the physics work here is that we have this uniform prior distribution to start over the ghost location, and then our sensor model says, when we're trying to predict the color of a given square, let's say the color of square 1, 1, the probability that that comes out to be yellow, or any particular color, is dependent on the goal, but it's not dependent on any of the other color observations. So once we know the goal, we don't need to worry about the colors of the other squares, right? So this, if we multiply 9 times 4 to the 9th, we get 2.3 million entries. So this is a really big probability table. That's not so big for like computers today, but like as these problems get bigger and bigger, it's going to be impossible to write out the whole joint distribution. So can we use independence here to help us? Are C11 and C12 independent? That's these squares here. So are the colors in these squares independent of each other? Shaking your head. Can I ask why you're shaking your head?
Because if the ghost is far away from both of them, then they'll both be like low.
Yeah, right. So if the ghost is far away from both of them, then they'll both be sort of that greenish, yellowish color. And if it's close to both of them, they'll both be sort of orange or red together. Like so you're going to see some correlations between these variables. You're going to see that like knowing one of them is going to tell you information about the other one. Right? So if I see the orange, I'm pretty sure that the yellow is like more likely than green might be for that bottom square because they're only one apart. So what about conditional independence, right? So we have the sensor model. It says that the color of a particular observation on a square depends only on the distance to the goal. So if I know that distance, if I know what the goal is, can I get away with this? Right? Like if I know the ghost is here, now are they independent? Well, they are, right? Because the orange one is we know how far away that is from the ghost, and we know how far away the yellow one is from the ghost. And it doesn't matter whether we sample the orange one from our noisy sensor or we sample a green one or a red one. It's of no consequence to predicting that yellow is probably going to happen in that bottom square. So now it's the case that yellow, the probability of yellow conditioned on goal being 2, 3 is the same as the probability of yellow conditioned on goal being 2, 3 and knowing the orange square. So now we do have conditional independence. Okay, so this idea of, we have this big model, it's exponentially large. We could write that down as a product of all these conditional probability tables like we did with the chain rule on the rain and the traffic example. But we don't want to do that because these conditional probability tables are going to get just as big as our joint distribution when we get to the last one, right? This one has so many different variables in it. But when we have conditional independence, we're going to be able to write this much more succinctly. Each one of these is only going to depend on one variable at a time. So that's really nice. So we go from exponential to linear. Okay, so that's the idea behind Bayes nets. And this lecture is about how do we do that in practice. So we're going to take these big joint distributions and we're going to try to succinctly extract the structure so that we can succinctly write them down as just a product of small conditional probability tables. Today's code is a Ghostbusters reference for those of you who've seen those movies, Ectoplasm. Okay, so everyone had time? Almost? Okay, it's on the website, so if you can't get the QR code, you can find it there. But yeah, so the big picture is this, right? It's a technique that uses this concept of like graphical models, which is really just models that use graphs, in order to encode the structure of the world and allow us to write down these concise, small conditional probability tables. So we're going to assume that each variable only depends on a certain small number of other variables, that there's this sort of like really sparse structure that's defining like how these things are hooked up. And that's going to allow us to represent these really large probability tables with a small number of conditional probability tables. Then we're going to be able to ask our model questions. So we can run these inference algorithms and ask for things like, what's the location of the ghost when I see all of these other observations? Or, what's the probability that it's raining outside when I see someone who has an umbrella? So the way that's going to work is we're going to use graphs. We love graphs in this class. So here's two different scenarios. One is where we're modeling the weather. The weather we're going to have basically these nodes in this graph are going to correspond to the variables in our scenario. So if it's just the weather, we have one node. It's just the weather node. And if it's this cavity example, we have a cavity node, one for the toothache variable, and one for whether this thing catches my cavities. Okay, and then the arcs between these nodes, these edges, are telling us about dependency relationships, right? Or in fact, actually what they're saying is if there's no arc between two nodes, then they are conditionally independent given their parents. So more on what they exactly encode later. For now, you can imagine that these arrows just imply causality, right? So the cavity causes the toothache, the cavity causes whether or not this thing catches my cavities. And so you can think of it as like causal arrows, right? Once I know this thing, I can predict the next thing. So go back to the coin flip examples. If I have n independent coin flips, what would my graphical model for this look like? Well, we have n variables, so we can write those down. And then we need to hook them up somehow. But they're independent, so we actually don't have any arcs. So this is the whole thing, right? They're strictly independent. And so we don't have any edges between them. So this is what the graphical model looks like. It's very simple for coin flips. Okay, now we can go back to this traffic example. Let's say that I write down two variables, traffic and umbrella. And I want to figure out, like, how does the edge go between these? Does it go this way? Does traffic cause me to take my umbrella? That doesn't feel quite right. Does me having an umbrella cause there to be traffic? Be kind of nice if I had that much power with my umbrella. But I don't think that's how it works either. So it really doesn't make much sense until we add this third variable that kind of causes both of them. And so when we write this down, it's obvious. Like rain causes traffic, rain causes me to take my umbrella. And so we can write down the graphical model like this. If we go back to the smoke alarm, we said that fire causes smoke. Smoke causes the alarm. So then we could write the graphical model like this. Or we could do this one for Ghostbusters, which says that the ghost location tells me the distribution over the colors that I'm going to see at each square. Right? So the variables are the ghost's location, the different colors, the different random variables representing the color that I observe at each location. And what we would like to calculate is the probability that there's of the ghost being at each of the locations conditioned on seeing the observations at all the squares. This is called a naive Bayes model. It's called naive because in general, if you make this assumption that everything sort of depends on one single variable, that's not going to work for you. But in this case, because of the way the sensor is designed, it'll work great. It's not actually that naive. But this is known as a naive Bayes model. We have one discrete query variable, that's the ghost location, and then we have all these evidence variables, which are the observations, and we're trying to figure out what the ghost location is conditioned on all the evidence. The evidence is conditionally independent given the query. Okay, so that's starting to get a little more complicated, but we can build these things up pretty large, right? So if I'm an insurance company, I might want to know, like, what's the potential payout that I would need to make? What's the cost, the expected cost of like medical liabilities and property for my different insurance for a particular person that I'm thinking about insuring, right? So I can ask them a bunch of questions. These blue things are things that I'm allowed to ask them. I can ask them about their driving record. I can ask them about whether they have their car in a garage, what their age is. I'm not allowed to ask them what their socioeconomic status is. In some states, you're allowed to ask gender, so you can actually discriminate against people with their gender for some reason. I'm not really sure why we're allowed to do that, but it is legal in some states. But other things are not legal, right? So, or you can't ask someone to, like, if you ask someone, are you risk averse? And you know that they're trying to get insurance from you, you're the insurance company, you ask them, are you risk averse? What would you answer, right? You're going to say that you're risk averse because that's going to give you a lower insurance premium. But you can ask someone whether they garaged their car and whether they have an anti-theft device and what's their driving record, and you can kind of get at this quantity especially when you know their age and you know what kind of car they're driving, you can kind of figure out what their risk aversion is, because maybe they buy a car that's especially safe, right? So you can get a sense of what this variable is based on these observations, and you don't have to ask them the thing that you know they're going to lie to you about anyway. So all these orange things you can't ask them about, and all these purple things are the things you'd like to try to calculate. And this is what insurance companies do. They have models like this. You can also use it to like troubleshoot your car if it won't start. There's all these potential reasons why it might not start. Let's say you observe it's not starting. You can measure, you know, whether the lights turn on, and you can try and get a sense of like why your car's not starting. I'm not going to sort of belabor that example. All right, so the way this works, how do you build a BaseNet? We sort of explained this a little bit, but let's get into the technical details. So each of these nodes is going to correspond to one of the random variables, and we're going to arrange them in a directed acyclic graph. Could look like this. And then we're going to have a conditional distribution for each node given its parents in the graph. Okay, so what does that look like? We have this table. It doesn't have to be a table, but if it's discrete, it ends up looking like a table. If it was continuous, then like maybe it's the case that like the ghost determines the hue of this color, but maybe the hue is like normally distributed in some range. So you could have this table could be like a mean and a variance of that Gaussian distribution or something. But yeah, keeping with discrete for now, we'll have a table for each of these entries. So G is going to have an entry for each location. It's going to be a uniform prior. And then each of these P of C conditioned on G's is going to have an entry for each location and an entry for each color, and then that's what our conditional table is going to look like. So this is exactly the same thing that we saw before when we had the traffic and the rain example, but now we have this diagram that's telling us which structure do we need to include so that we don't have all that redundancy. And so we're going to have one of those for each color. Right? So a BaseNet is this topology, the graph, and it's also this local conditional probability table that's telling us how do these things relate to each other and what depends on what. Okay, let's try that with an example. This is the idea of like I have an alarm in my house, and this alarm is pretty good at detecting burglars, but it also sometimes tells me when I have earthquakes in my house. But I'm actually never home, right? So I need my neighbors to call me when my alarm goes off to let me know that my alarm's going off, right? So maybe I'm always working or something, right? So I have all these variables. There's a burglary variable. Did it happen? Was there an earthquake? Did the alarm go off? And then did I get a call from my neighbor John, or did I get a call from my neighbor Mary? This example comes from Udea Pearl. Okay, so I can model that like this, right? The burglary causes the alarm to go off. The earthquake causes the alarm to go off. And my alarm going off causes my neighbors to call me, right? So that's how the arrows go. Does that make sense? Questions on this so far? Yes? Is there a reason why there's two different neighbors? Yes, there is, but we'll get to that in a second. So they'll have different sort of probabilities of calling me. Right, so let's write down some conditional probability tables. This is just the structure. This isn't the whole BaseNet. The BaseNet is this plus we have to go to these conditional probability tables. So the probability that there's a burglary maybe is like 1 in 1,000. Let's say that this is where Udea Pearl lives in LA. Then there's the probability of an earthquake, which maybe is 2 in 1,000 for LA. And then given these two variables, we can write down the probability that the alarm goes off, right? The alarm is very likely to go off if there's both an earthquake and there's a burglar. It's also quite likely to go off if there's just a burglar and no earthquake, right? If there's only an earthquake and no burglar, it's maybe 3 out of 10 it's going to go off. And then if there's nothing, if there's no burglar, no earthquake, let's say that there's a 1 in 1,000 chance that like a mouse bumps into the alarm and causes it to go off. Okay, and then there's two neighbors, right? There's John and there's Mary. Let's say that John is 0.9 likely to call when the alarm goes off, and also 0.05 likely to call just for no reason. Maybe listening to the TV, or there's some reason he thought the alarm went off. maybe Mary is hard of hearing, so she can't hear the alarm, and so there's only a 0.7 chance that she calls when the alarm goes off. But she's less likely to call when it's not going off because she's better at focusing or something. I don't know. Right, so we can write all that stuff down, and that allows us to express this large conditional probability table using only these a small number of parameters. So how many parameters? Well, there's one for each of these because, remember, once we know one of those values, the other one has to sum to 1. So we have 1 for each of these top 2 tables. We have 2 for each of these bottom 2 tables, 2 parameters, and then we have 4 parameters in this middle table, a total of 10 parameters. So if we were going to do this the hard way, where we write down the whole joint distribution, we have 5 different binary variables. So that's 2 to the 5th parameters minus 1 because they have to sum to 1. So 31 parameters instead of 10. So already for just 5 variables and just binary, this is saving us quite a bit. So the Bayesnet semantics are essentially that this allows us to write down these conditional probabilities conditioned only on the parents of each node, and then we can multiply those things together to construct our joint distribution without any loss of fidelity. This exploits the sort of sparse structure, so we're assuming that the number of parents is usually small. Okay, so I already sort of alluded to this, but the size of a Bayesnet is going to be a lot smaller than the size of the joint distribution. So the joint distribution over n variables, each of which has d values. Does anyone know what that would be? Yes? D to the n. Yeah, great. And what about an n-node Bayesnet if the nodes have at most k parents? And let's say they still have d values. So I need a conditional probability table for each variable. They have k parents, and there's d values that each variable can take on. What would one of those conditional probability tables be like? Yeah. D to the k, yeah, and we have n of them, so we need n times d to the k. So this gives you the power to calculate the whole joint distribution, but if you have a lot of sparsity, if k is small, and you know what d is, then this goes from exponential to linear, which is really great. It's also easier to write down these conditional probability tables than it is to write down the full joint distribution. Like if I said, what's the probability of it being rainy and me having my umbrella and there being no traffic? Does anyone know what that probability would be? I think it's safe to say that nobody knows what that probability would be. But if I say, I know that I am more likely to take my umbrella when it's raining, and I know that it's more likely for there to be traffic when it's raining. So now I can sort of define these conditional probability tables more easily than I could if I was trying to define the whole joint distribution. So it makes things easier. And we'll see next time that it can give faster answers to our questions about probabilities. So here's a question about a probability. What is the probability that there's a burglary, and there's no earthquake, and the alarm goes off, and neither John nor Mary calls? Stare at this for a second and see what you think. Because we have all the answers here, right? We can construct the joint distribution from this information. I'm not sure why there's a 33 on the slide. Ignore the 33. So what we can do is we can highlight all the relevant quantities in these tables. Right? So we highlight all these things, right? So first we know that there's a burglary, then we know that there's no earthquake, we know that the alarm does go off, true. We know that John doesn't call, we know that Mary doesn't call. And so the probability of the burglary is 1 in 1,000. The probability there's no earthquake is 0.998. Then this probability says condition on there being a burglary and no earthquake. What's the probability the alarm goes off? It's 0.94. Then we can get the probability that John doesn't call, given that the alarm Seems like that should be a true. Not sure why it's on the false. Oh yeah, because the alarm is true, and then John doesn't call, right? So condition on the alarm being true, neither of those two people calls, and so we multiply all these orange quantities together, and we get 0.000028. Nice. So then we would just have to do that again for each of the 32 other values in our table, and then we would get our whole joint distribution. So we can compare this idea to this idea of the chain rule, and we see that it looks very similar, right? Before we had the chain rule, we were just multiplying by all the variables that came before that variable. Now we're saying, yeah, we just need to multiply by all of the parents of that variable in this Bayes-Net structure. So we can assume that these xi's are sorted into some like topological ordering, but the Bayes-Net asserts the conditional independence of x from all the other factors that are not the parents of x. Right? So we're saying x is conditionally independent of all of its non-descendants. So once I know x's parents, right? Once I know these two things, if those are the parents of x, then now I know that, like, here, let me use a better color. None of these variables influence x. Nothing up here can influence x. X is conditionally independent of all of its non-descendants given these parents. Okay, yes, question. It's conditionally independent of all of its non-descendants given its parents. So if you know U1 and you know UM and you know all the ones that are in between, all of these parents of X, right? Like we could have like there could be a U2 in here, right? And that could also influence it. But if you know all of these things in this red and now blue circle, then anything in these other regions that are outside of this sort of shield, this like blanket, you're independent from, conditioned on those parents. Yeah? X had another parent that's called U3? Oh, U1 had a parent that's like, let's call it V, right? So V is a parent of U. That's what you want to know? Yeah, it's not descended from X because it is like an ancestor of X. Yeah. Or it could be sort of unrelated to X. So in the coin flip example, all the coins are independent of each other just because there's no connection between them. Okay? Other questions? All right, nice. So let's look at this burglary example again. We'll get rid of the John and Mary calling just to make the problem a little simpler. Let's try and figure out, like, how would we figure out the structure of this Bayes-Net? Well, we could start by just, we have the first variable, burglary, right? There's no other variables yet, so we're sort of good. But now we want to add in the next variable, and we want to decide, like, is this the relationship? Does the burglary cause earthquakes? That doesn't feel right. So maybe we want to say that like the burglary and the earthquake are independent of each other. If they're independent of each other, then we can say that we're good so far. Like we have drawn all the arrows that we need to draw. It also doesn't feel like earthquakes cause burglaries, right? Although I guess there's certain models where you might think that they would. We could add the alarm to the picture, and now we say, okay, well, now that the alarm's in there, it makes sense. Like burglary causes alarms, probably. Earthquake causes alarms, probably. And then we can sort of write down these conditional probability tables, and then we're back where we were, right? So what if we write them down in a different order? What if we start with the alarm variable? We can just kind of pick which order we want to put them in. So we put the alarm variable. That's fine by itself, but now we want to add the other variables. So we put the burglary variable down. Is burglary conditionally independent of the alarm variable? Well, are they independent, just like strictly independent? No. I see people shaking their heads, right? There should be some kind of an arc here. We don't know if it points this way or if it points the other way, right? And then if we add the earthquake variable in, what is the relationship between the alarm and the earthquake? Are they independent? No, right? So the alarm and the earthquake, again, we don't know necessarily which direction these arrows go in, but we know that there's got to be an arc between these two things. And then what about burglaries and earthquakes? Well, we might be tempted to say, okay, we know that like before we had these arrows pointing in other directions and like we knew that everything was fine. Like, why do we have to think about this arrow? But let's say that I have this setup. If I find out that there's a burglary, does that tell me whether there was an earthquake or not? If I know that the alarm went off, right? So I know the alarm went off, and then I find out that there was a burglary. Do I think it's more or less likely that there was an earthquake now? Well, probably if the alarm went off and I know there was a burglary, it probably went off because there was a burglary, right? So in some sense, this burglary variable like explains away this concept of the earthquake going off, right? Like, so if I have burglary and I know the alarm went off, this like decreases my likelihood of there being an earthquake just because the burglary is a sufficient explanation for the alarm going off. So these things are not necessarily conditionally independent once I know the alarm, because the burglary can explain away some of the earthquake probability. Does that make sense? This is kind of a difficult concept to get sometimes. Yes? Yeah, so that's a good question. So you said it applies in the opposite direction, so do you need two different arrows? So in a BaseNet, you can kind of choose. The directions of the arrows, we've said so far that they sort of represent causal directions, like this one causes that thing. But it's really not quite the case that that's what they signify. So you don't need to pick the right direction in the causal structure. So it can be either direction. You could start with earthquake and do an arrow to burglary as well. Really what that's saying is that conditioned on alarm, burglary is not independent of earthquake. And so the arrow can go in either direction. Those would be two different models though. So we'll get to that in a second. So like depending on which direction the arrow goes, you get two different models. But so yeah, so we could write down our conditional probability tables here. But what we're going to do when we try and write these down is we're going to run into some trouble here, right? So like the fact that we have these tables, like what's the probability, given that the alarm goes off, of there being a burglary? Well, that kind of depends on the earthquake, right? Like if there was an earthquake, then that changes the probability. So it's harder to write down this number. And similarly, if we know that the alarm went off and there was a burglary, what's the probability of the earthquake? Like that's also kind of hard to think about. So because we've written things down in a non-causal direction, it's hard to estimate these conditional probability tables. It would be much easier if we had the sort of right causal structure. Okay, so here's another example of that, right? Let's go back to this traffic situation. Let's say that we only care about rain and traffic. I'll get rid of the umbrellas. So is it the case that rain causes traffic, or is it the case that traffic causes rain? Right? So if rain causes traffic, then when the rain cloud arrives, it causes the cars to slow down because they don't want to hit each other. If the traffic causes rain, then the minute this person stops being so close to the other car, I don't know, the rain cloud gets caught behind the wheel or something like that. So like this is a potential model of the world. It doesn't necessarily mean it's a good one, but traffic could cause rain. We have this joint distribution which tells us like we see rain and traffic together 3/16 of the time, we see rain and no traffic 1/16 of the time, etc. If we wanted to model these two different Bayes nets, we could do that. We could write down conditional probability tables. We could say that, okay, well, if we just say that rain is independent, it's its own variable, it maybe rains a quarter of the time. And then we have our conditional probability table that says, if it's raining, then there's 3/4 likelihood to see traffic. And if it's not raining, it's 50-50. That sort of makes sense. But there's an equivalent interpretation, which is that traffic causes rain. And this set of tables is actually totally consistent with the same joint distribution. So we can say, all right, there's 9/16 probability of traffic and 7/16 probability of no traffic. That happens sort of just independent of anything. And then once we know traffic, we know that there's, if we see traffic, rain is 1/3 likely. If we don't see traffic, rain is 1/7 likely. And if this is the case, you end up with the exact same joint distribution. But it's highly non-intuitive why like these would be the numbers that you would see. So these are two different ways that you can model the causality relationships between these variables. Okay, does that make sense? The arrows can go either way. We get to choose. So we got to try and choose them correctly. Questions? Okay. So yeah, this question of causality, right? Like the Bayes net, when it reflects the true causal patterns, it's easier to write down the conditional probability tables. It makes more intuitive sense. It simplifies the connections. We end up with fewer edges often. And it's often easier to elicit these probabilities from experts because experts kind of have a sense of like how things work. And that model is a causal model generally. So they don't need to be, the Bayes nets don't need to be causal. We can write them down in either direction of causality, but it's sometimes is harder to write them down. So like the traffic and rain example, or we end up with arrows that just reflect correlation and not causation. Sometimes it's the case that there is no causal model of the domain because we're missing some variables. So the idea here is that like we have these, we want to build up these Bayes nets. We want to like encode all the structure of the world. That's going to help us with modeling these probabilistic questions. But if we build them up in such a way that like we don't capture one of these variables, that might be okay. It might still be a good approximation of real life. But if we're missing certain variables, we might not capture all the causality relationships. So what the arrows really mean, you can think of them as causality, but you should be careful because like it might be the case that they don't encode causality. Really, they encode conditional independence. So when there's an edge, you know that there's a dependence relationship, and when there's no edge between two variables, they're conditionally independent given their parents. Okay, so let me summarize so far. Right, so we have this idea of independence and conditional independence. These are important forms of probabilistic knowledge. They're going to help us to write down and express these complicated joint distributions over large probability models. A Bayes net is just going to allow us to encode that really succinctly so that we can go from this exponentially sized thing down to a linearly sized thing. And when we do that, that means that we can store these things in memory, and it means that we can query them more efficiently as well. So that's the next thing that we'll talk about. But the most important concept that I think I want to try to communicate to you is that this allows us the flexibility to trade off between model accuracy and this memory compute efficiency, right? So we started with this coin flip strict independence style model. That's not a very good model. If we do that, we saw that even in the traffic and rain and umbrella example, we could no longer model the joint distribution by assuming all the variables were strictly independent. From there, you can add a little bit of structure. You can get to a naive Bayes model. This allows you to ask questions about like some query variable A conditioned on a bunch of evidence. And then you can add more and more structure. You get sort of like these sparse Bayes nets, like the earthquake example. And then you can get the full joint distribution, where A affects everything, B affects C, D, and E, et cetera. And if you have this structure, this is sort of like the full generality, but now you have this exponentially large probability table, whereas here you just have a small number of linear conditional probability tables. So this spectrum, going from strict independence to the full joint distribution, is kind of like the space of probability models, and where you end up landing in this space is sort of up to you as the modeling person, right? Like you get to decide as the designer, what is the right way to model this problem? Do I have enough memory that I can afford the full joint distribution, or do I need to, restrict my model? And if I'm restricting it, how should I think about the probability and the causality relationships and the conditional independence between the different variables so that I can model this effectively? So when we put our designer hats on and we're modeling the world, this is a tool in the toolbox. Okay, questions so far? Yes? Can the Bayes net be a cyclic one? No, we're going to restrict it to just be a DAG, a directed acyclic graph. Yeah. And the reason for that is you need to sort of think about this idea of the chain rule, right? So we have this joint distribution. What are we trying to do with our Bayes net? We're trying to model this joint distribution. So if I have A, B, C, D, and E, right? The joint distribution says that the probability of A times the probability of B conditioned on A times the probability of C conditioned on A and B times the probability of D conditioned on A, B, and C times the probability of E conditioned on everything else gives me the joint distribution again, right? So there's no reason when we have this chain rule that we would need there to be a cycle, because as long as you go in order A, B, C, D, E, then every variable can at most depend on all of its predecessors. And you can work out the chain rule, and then you get this acyclic graph. So this is an acyclic graph that's got directed edges that captures the whole joint distribution, and that's sufficient. So worst case, you can always write this down, and that's a valid Bayes net. Okay, question.
What's the difference between the naive and the sparse Bayes net again?
Okay, yeah, great. So what's the difference between naive Bayes and sparse Bayes net? So the idea with this isn't like an official name. This is just like the concept of a Bayes net with sparsity. So the idea is most of the time when we're writing down Bayes nets, we're hoping that each parent has a small number, or sorry, each variable has a small number of parents. So that's sparsity. And then in the naive Bayes model, we're saying that there is exactly one variable that is sort of independent of all the other variables, or sort of causally doesn't depend on any of these other variables. And then conditioned on that first variable, which is generally the query variable, you can think of this as like, where's the ghost in the Ghostbusters example? We have all these other evidence variables. So this is like, what did I observe at square 1, 1? What did I observe at square 1, 2, et cetera? And the naive Bayes model is just set up so that there's one parent, and all these other variables are like evidence variables. So this is a type of sort of sparse Bayes net, because all the nodes have at most one parent. But it's sort of making an even further assumption, which is that there's one query variable and the rest are evidence variables. So if we go back to like the car insurance example, this one, right? So we have 3 query variables. We want to say, what's the medical cost, what's the liability cost, and what's the property cost of me insuring this particular person? And we have a bunch of evidence variables. We can ask them their age. We can ask them how long they've been driving for. We can ask them what their driving record is. Do they have any accidents? This anti-theft thing is nice because it tells us, like, for one thing, we know that it deters theft, right? So if we ask them if they have an anti-theft system, that tells us about this variable, which eventually will flow into the property cost. But it also tells us about their risk aversion, right? So if they're the kind of person who would buy an anti-theft device, then we can go backwards and get this risk aversion variable in some capacity. So this would be like somewhat sparse BayesNet. And then you can get sort of more or less sparse depending on how connected you make these different pieces. Does that answer your question? Okay, other questions? Okay, so we have about 10 minutes left. So let me, what do folks want to do? Do you want to stop there, or do you want to go on to inference? Like, how do we ask these models questions? We have 10 minutes left. Would it be helpful to keep going, or should we stop? Hands up for stop? Okay, hands up for keep going? All right, cool. We'll do inference next time.